today is radio frequency circuits. So the outline is, first we will have the high frequency effects. Second, we will be talking about radio frequency amplifiers. Then the learning objectives are, first, learn about radio frequency circuits. And second, learn about high frequency effects. And third, learn about radio frequency amplifiers. So let's start with the high frequency effects. So when you first began to study electronics, you probably divided the frequency spectrum into two parts, AC and DC. Okay, so a capacitor, for instance, would be considered an open circuit for DC and short for AC. This simplifying assumption works well in arriving at a general understanding of an audio amplifier circuit and in calculating its gain at mid-band frequency. So later on, you needed to be more careful in considering the effects of the frequency. The bypass capacitor that looked like a short circuit at 1 kHz, for instance, would no longer simple at 20 MHz. Perhaps an amplifier contained a transformer or other inductive element. Again, at first approximation, it might simplify an inductor as an open circuit for AC and short circuit for DC. So that is a transformer that would be represented as an ideal. Further investigation, however, especially at extremes of the amplifier frequency range, might reveal that the need to consider not only inductive reactance, but also losses in the iron core of inductor or transformer. So it is easy to say that the characteristic of these active components changes with respect to its frequency. So all electronic devices, whether active or passive, have capacitance and inductance that are not included intentionally, but are inevitable result of the design and construction of the component. A capacitor, for instance, so if we have this capacitor, will exhibit inductance and resistance as well as capacitance. It can be represented by this equivalent circuit here. The series inductive component Ls is mainly due to the leads. The resistive components can be divided into two parts, so smaller resistance, a small series component of Rs due to the lead resistance, and a large parallel resistance Rp representing dielectric loss. So mura siya kung ikuan nimo siya, abilang nimo siya ordinary capacitance, but actually it has this equivalent circuit here. So na siya inductive component, na po siya capacitive component. So as the frequency increases, so does the inductive reactance. Meanwhile, the capacitive reactance of the component decreases with increasing frequency. Eventually, a point will be reached where two reactances are equal and the capacitor becomes a series resonant circuit. So this point is called self-resonant frequency, whenever the two reactances meet or they are equal. So similar effects occur in transistors. Consider an ordinary bipolar transistor such as 2N3904, this one, for instance. Each of the two junctions has capacitance here, drawn in between the base and the emitter, and between the collector and the base, as shown here. As frequency increases, the capacitive reactance will decrease until the performance of transistor is degraded. The base to collector capacitance, for instance, will cause feedback from output to input in an ordinary common emitter amplifier circuit. The feedback can lower the gain of amplifier or cause it to become unstable. So this capacitive reactances with this BGT can really affect the performance of the circuit. At low frequency, we generally assume that capacitors have capacitance, resistors have resistance, and short sections of good conductors. We saw that in previous. This assumption is really simplification that becomes less accurate as the frequency increases. For instance, a circuit board trace has a small amount of inductance in addition to resistance. So this is just an example. There will also be capacitance between this trace and every other trace on the board. So imagine in a circuit board, these circuit board traces have this innate value of resistance, inductance, and capacitance. So a little thought will show that the inductance and capacitance related to this trace cannot be shown exactly by single capacitor and a single inductor. In fact, no finite number of lumps of capacitance and inductance will do, since they are distributed along the entire length of trace. We can often approximate these distributed constants by a few lump constants with reasonable accuracy. But you need to remember what is really happening, because some problems can be solved using distributed constants. So here in this figure, give you the idea how an ordinary circuit board trace might look when analyzed this way. So based on my experience in designing, we usually in designing we are not consider directly the value of this package resistance, capacitance, and inductance. But as you design and in the long run, you must really consider those, because it might affect the performance of the whole system of the circuitry. So you can refer to it in those data sheets given by those packaging specifications. So this is just an example. It is possible to design a circuitry to reduce the effect of stray capacitance and inductance resulting from wiring and circuit board trays themselves. In general, keeping the wires and traces short reduces the inductance, and keeping them well separated reduces the capacitance. Then also inductive coupling can be reduced by keeping conductors and inductors that are in close proximity at right angle to each other. And also the use of toroidal cores for inductors and transformers also helps to reduce stray magnetic fields. Actually, there may seem to be contradiction here. For instance, how do we keep components far away from each other while simultaneously keeping connections short? Obviously, compromise is necessary. So there is a necessity of trading off. So naay ginaingon nga dili nimo maangkon tanan. So naadjud kay prioritize. So asa man ang i-trade off nimo, ang kalayon ba nila or ang kadulon? Kay kung mas malayo sila, mas less ang kung mas short siya, mas less ang inductance. While kung ipalayo nimo sila, less ang capacitance. So asa ang imong i-trade off? It is based on your priority or specification or target goal for that circuitry. Then another way to reduce interaction between components is to use shielding. So coupling by way of electric fields can be reduced by shielding sensitive circuits with any good conductor.